Alright, so in this video we're going to be talking about the central limit theorem and its significance and its proof. So to start, the central limit theorem is no matter what data you have, if you have a certain amount of trials and a general value accepted is your trials should be greater than or equal to 30. If you find the averages of every single trial and plot them, they will share a normal distribution, tend towards a normal distribution as n approaches infinity. So over here I have 4 different probability density functions, and the central limit theorem applies for all of them. So imagine we have in one trial just 20 different data points, and we find the average, and it happens to be around here. And then the next trial we have some more data points, and the average is around here, then maybe here, 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 and there. If the central limit theorem is stating that as the amount of averages you find approaches infinity, no matter the distribution, whether uniform, exponential, or any other shape, its distribution will start to follow a bell curve. So, what is the significance? You see, it's not always in analysis or statistics where we know the distribution of the data we are collecting. So the central limit theorem at least gives us some information that we can work off of. If we don't know the distribution of the data, we can at least work from the central limit theorem knowing that their means are going to be normally distributed. And from this we can do t-test analysis, for example. Now, moving on, just want to move on to a separate page for a little proof. This is a very complex proof, so I'm just going to breeze through it, but the central limit theorem proof is we're finding that the moment generated function equals the expected value of e to the tx. And we know that the expected value is its inner variable times its probability function summed up. And what we can do is, if we're finding the expected value of e to the tx, we show our probability density function of a normal distribution, and we integrate it as we multiply by the constant of e to the tx. And using some algebra, we find that the base e, we can add them into the exponent, and we get negative 1/2 x squared plus tx. And then we can complete the square, and we find that we have e to the negative 1/2 times x minus 2 squared minus t squared. And this is all integrated above all free space with respect to x. And finally, we can pull out e to the t squared over 2 and multiply it by the normal distribution. And we know that because it shares a normal distribution, it's going to be equal to 1, and we're just left with the moment generating function equals the expected value of e to the tx, which equals e to the t squared over 2. So all in all, we can confirm that no matter the distribution of data it shares, their means share a normal distribution.